Hi, welcome back to Quantum Field Theory, a student's perspective. Today's lesson will continue with the path integral, and we'll do it for the harmonic oscillator, which, if you've gotten this far in physics, you kind of know is the probably the most important system. It's the only system we can usually treat exactly in physics other than the free particle. And a very famous physicist, Sidney Coleman, who passed away a few years ago, but he once wrote, "The career of a young theoretical physicist consists of treating the harmonic oscillator in ever-increasing levels of abstraction." So let's start treating the harmonic oscillator. And as usual, we write down the Hamiltonian, h of pq, standard p squared over 2m plus 1/2 m omega squared q squared. And last time when we left, we wrote down a formula for the vacuum or ground state to vacuum transition amplitude in the presence of a driving force F. And we wrote it as a path integral, the integral over d. And if you notice, we have, once again, we have this funny capital D because the measure in these path integrals is very ill-defined, and it gives mathematicians heart attacks. The integral of dp dq, then e to the I integral, I'll put the boundaries, but it's not really necessary, dt, infinite past, infinite future, and pq dot minus 1 minus I epsilon. I'll explain this epsilon in a second. H, all right, plus fq. So this epsilon is designed to enforce boundary conditions, and we talked about it, and it's equivalent. You know, we're going to just always make the substitution here. M goes to 1 plus I epsilon m, and m omega squared goes to 1 minus I epsilon m omega squared. So this is just to make things converge, and you know, it's the type of thing physicists do, and we'll worry about it later. Now, because the path integral is quadratic, h is quadratic and p squared, and the forcing term only involves q in this situation, we can integrate out the momentum degrees of freedom, and we'll get the original Feynman Lagrangian formulation of the path integral. 0, 0, 0, f is the integral of dq e to the I, the integral from minus infinity to infinity, dt, and then this whole thing in bracket, 1/2 1 plus I epsilon m q dot squared minus 1/2 1 minus I epsilon m omega squared q squared plus fq. And this is our forcing term. And for the rest of this lecture, we're going to make things a little easy. We're just going to set m equal 1, so we don't have to worry about it. And the next thing we're going to do is we're going to do Fourier transforms. And this is all fairly standard things. So we'll define q tilde e is equal to the integral from minus infinity to infinity dt e to the I et q of t. So this is the transformed coordinate, and we can likewise invert that. We get the integral from minus infinity to infinity dE over 2 pi e to the minus I et q tilde e. So, and we have the same for f the same way. Same q, we could put like f there, ft and f tilde q. And so when we substitute these things in this bracket, we're going to get 1/2, and it's just a routine substitution. Oops. The integral from minus infinity to infinity dE over 2 pi dE prime over 2 pi e to the minus I e plus e prime t. And the reason why we get different variables is because when we have the q's there, you know, we use one q and q dot brings down an e, but from here q dot brings down a minus IE, but we can't use the same e. You know, when we do another q dot, we have the e prime. And then we have a minus 1 plus I epsilon e prime minus 1 minus I epsilon omega squared. Remember, we set m equal 1. And so this whole thing multiplies q tilde e, q tilde e prime. And then I have plus f tilde e, q tilde e prime, plus f tilde e prime, q tilde e. We get two terms because I took a 2 out in front and I just made it symmetric. And so this is the only thing that depends on t. When we substitute it in to that integral minus infinity to infinity of dt, we're going to get a 2 pi delta e plus e prime. And then we integrate over e prime, and we're going to end up getting our action s is equal to the integral from minus infinity to infinity of dt. That's equal to 1/2 the integral dE over 2 pi 1 plus I epsilon e squared minus 1 minus I epsilon q tilde e, q tilde minus e. Then I have plus f tilde e, q tilde minus e, plus f tilde minus e, q tilde e. Okay, so I will come back on the next video and we'll continue substitute this into the measure and evaluate it. We'll see you next time. Bye-bye.